Right, let's talk about enantiomers. When you have two non-superimposable mirror images, that's when you have a chiral molecule. And technically speaking, when the molecules are non-superimposable onto each other, you do have enantiomers present. This is, in essence, the definition of an enantiomer. The mirror image cannot be superimposed onto each other. So the 1-chloro-1-fluoroethane example that I showed in an earlier video, that's a perfect example of this. Take the mirror image of the first molecule, rotate it so that you have the same overall geometry, and try to superimpose it. And if you can't do it, then that tells you this molecule, the two molecules in fact, are enantiomers of each other. This is the one of the techniques that you use to determine if the molecule is chiral. Now, for small molecules, this is definitely helpful, but it can get tricky when you have bigger molecules. So I'm going to show you, right, so this one doesn't match. So I'm going to show you a few techniques to try to get around the idea of determining whether something is chiral or not. So what we're doing right here is we are changing the molecule such that it coincides in geometry, right? So we only have the hydrogen pointing to the left, and we have these two groups pointing to the right. So this is the method of switching. And what we're going to do is simply switch two groups at a time. And we're going to keep track of how many times that happens on the second molecule to make it look like the first molecule. So what I'm doing here is noticing that the methyl and fluorine groups are different in the second molecule. So what we're going to do is simply switch them, switch their positions. And that switch that just happened, counts as one switch. And what you'll notice right now is that this second molecule, the mirror image, when I underwent that one switch, makes me now have the first molecule that I started with. And this is basically the rule. When you end up with an odd number of switches, on your second molecule to get to the first, you are dealing with the enantiomer of the first molecule. But if it took you an even number of switches to, go from the second molecule to the first, you have the same molecule at hand. This is actually most useful when you are presented with two versions of the molecule and you have to compare them to each other to determine if they are enantiomers or not. So you can rotate the second molecule so that it lines up in geometry with the first one, and then you start doing your switches to see if you have the same molecule or not. Um, so this is one of the techniques of finding out enantiomers, right? So odd number of switches, enantiomer; even number of switches, same molecule. And the switches always have to happen between two groups. The other technique is to use what I like to call Half-Newman projections. And the idea is that you want to look at the molecule from the opposite side of what you'll find out to be the lowest priority group. But in molecules like this, technically from the opposite side of where the carbon-hydrogen bond is located. So we're going to eventually build up to the true nature of this a little later. But if you look at the carbon center, specifically opposite from where that carbon-hydrogen bond is, and this is now your point of view, what you are going to determine is that, okay, so here's the mirror that we're having as reference. What you'll see is that from this point of view, the molecule on the left, the methyl group is pointing towards us, the fluorine group is pointing away, but from the point of view presented here, the methyl group has to be pointing to the left side of the molecule, the fluorine has to be pointing to the right side, right? So think of this as you being present right on that side such that you don't see the carbon hydrogen bond. You're exactly opposite of it. Over here, if you are opposite of that carbon hydrogen bond, then the fluorine is going to look to you to be on the left side and the methyl group is going to look to you to be on the right side. So your Half-Newman projections will look like this. And once again, you don't see the carbon hydrogen bond because it's directly on the back, directly opposite of your point of view. The chlorine on both molecules is sticking upwards, right? So you just have it pointing up, and this is your typical Y down shape. So with the Half-Newman projections, you can tell, oh yeah, look at that. definitely you have a different picture going on right here. The methyl is on the left side on this Half-Newman projection. The methyl group's on the right side on this Half-Newman projection. So these are not the same things. They are enantiomers of each other. So that's overall 3 techniques to determine whether something is chiral or not. You could look at the mirror image, um, or if you don't have the mirror image, you can draw the mirror image of the molecule and try to superimpose it. If that doesn't happen, you get yourself enantiomers. Otherwise, you could do the switch method to determine if you have enantiomers, or alternatively use the Half-Newman projection. So 3 different ways of doing the same thing, and in different situations, one method may be better than the other. But now let's introduce the Cahn-Ingold-Prelog priority rules, since we have now an idea of how to distinguish whether a carbon is going to be chiral or not. As I mentioned earlier, when you do have a chiral carbon, you do have 2 sets of enantiomers, or excuse me, 1 set of enantiomers present. And you can't just call them both the same thing, because it makes it ambiguous as to which one you actually are dealing with. And as it turns out, chiral carbons, enantiomers, um, when pure, they have different properties, especially if we're talking about drugs. Different enantiomeric drugs have different outcomes in drug delivery. Sometimes one chiral enantiomer um, could have a benefit, medically speaking, to you, whereas the other one could be quite the opposite, could be quite toxic. So it's important to have the one enantiomer and only the one enantiomer, and also to be able to refer to it exclusively. So we're going to introduce the Cahn-Ingold-Prelog priority rules to give each one of those molecules a unique name. And the way this goes is basically we first determine that there is a chiral center present in the molecule. If there are no chiral centers present, then you don't have uh, stereoisomers. But if there are chiral centers present, then we ask the question now, um, what kind of atom is bonded to the chiral center? Specifically, which out of the atoms bound to it has a higher molecular weight? If there is one that has a higher molecular weight, automatically that has the highest priority out of the 4. If none of them um, have it, then we're going to have to ask a few other questions. But uh, the atoms that do have lower molecular weight compared to the one that has higher molecular weight have a lower priority given. And what we do ask for those is, um, okay, well, what happens when we look at the next neighboring atom? Um, does that neighboring atom have a higher molecular weight? Yes or no? And you basically keep doing this and working your way further and further out into the molecule until you find a section in which you can make the distinction in terms of the molecular weight question. And even though this is kind of like a nice diagram, truth be told, going through the examples is what's going to make sense as to what this is. And the flowchart here is going to be almost an afterthought, as you're going to find out. So let's take a look at this molecule once more. You will have 4 things bound to this chiral carbon. We have hydrogen, we got chlorine, we got fluorine, we got carbon directly bound to the central carbon. Out of all 4 of those things, chlorine is the one that has the heavier atomic weight, right? This is about 35.45 grams per mole. Fluorine is about 19, carbon is about 12, hydrogen is 1. So chlorine definitely wins that round. That is the highest priority. After that, fluorine follows because that's 19. Carbon is only 12, but carbon is still higher in priority than hydrogen, which is only 1 gram per mole. So this is how you assign the priorities. And as you can see, the flowchart is kind of an afterthought, but I'm going to keep it here just to kind of give you an idea of how we are analyzing the molecule. Now for the enantiomer, it's still the same thing. Chlorine is the higher priority, fluorine is the second highest priority, the carbon of methyl is the third priority, and hydrogen is the last priority. So what we do now is I'm going to switch over to the Half-Newman projections, and putting back the priorities in here, what you basically do is, from the point of view opposite of the lowest priority, and in this case the lowest priority is the hydrogen group, right? So we're looking opposite of that carbon hydrogen bond, as I was pointing out earlier. You basically look at how the going from priority 1 to priority 2 to priority 3, how that rotation takes place. And what you see here is that the rotation in the left molecule is clockwise, whereas in the molecule here on the right, the rotation is counterclockwise, going from priority 1 to priority 2 to priority 3 and back to 1. So this is what makes the distinction. The rotation going clockwise is what we call an R rotation, whereas the rotation going counterclockwise is what we call an S rotation. And this ultimately comes from the German words for clockwise and counterclockwise. So R goes for clockwise, S stands for counterclockwise rotation. And when we have that, we have basically come up with the proper unique names for these two molecules. The one here on the left side with the clockwise rotation based on priority 1, 2, and 3 groups is the 1R. And so what we do is, in front of the molecule, in front of the entire name of the molecule, in parentheses, we just say R. And here I'm just writing the 1 to depict that the chirality center is on that first carbon. But as you're going to find out in your textbooks, you could even just write this as parentheses R only without the 1 in front. And since there's only one chiral center here, it's understood that that's where the R configuration must happen. Same thing here. You could either write this as 1S or just regular S, still in parentheses in front of the entire molecule, and that tells you the entire story. So at this point, both molecules now have unique names, and we can definitely refer to them exclusively without any ambiguity. Alright, so in the next video, I'm going to show you a set of examples where we're going to do the same thing, and we're going to be looking for these chiral centers and determining the priorities of different groups. And these examples are going to be a little bit more difficult than the one we just did. So I'll see you in the next video.